Assalamu alaikum guys, welcome back. So in this lecture we are gonna talk about the oxygen dissociation curve of hemoglobin. This is the curve for dissociation of oxygen from oxygenated hemoglobin and then subsequently loading of hemoglobin with oxygen. All right, it has a general sigmoid shape, okay, an S-shaped curve. An S-shaped curve is formed, and that is due to the cooperative binding of hemoglobin, binding of the heme groups in the hemoglobin to oxygen molecules. All right, and we've discussed about the cooperative binding in the previous lectures, in which I told you what the cooperative binding was, and you guys can check the link to that lecture in the description. This is what we discussed in the previous lecture. A link to that lecture is given in the description, so do check that out if you haven't. All right, anyways, now let's look at the oxygen dissociation curve. Okay, so basically ignore this part for a while. First, let's talk about the oxygen dissociation curve, and then I'm going to explain what P50 really means. Okay, so basically, as we discussed in the last lectures, that hemoglobin can attain two types of conformation. It can attain an R conformation and a T conformation. The T conformation is the tight or tense conformation, whereas R is the relaxed conformation. R has a higher affinity for oxygen. R has a higher affinity for oxygen, and T has a lower affinity for oxygen. And so T is the tense form of hemoglobin. So it can easily release oxygen because of low affinity for hemoglobin for oxygen, whereas R can easily accept oxygen. Now, this is if we start out from here, from the portion, the partial pressure of oxygen in the lungs, what happens here is that the hemoglobin gets 100% saturated, meaning all the four molecules of oxygen have been accepted by the hemoglobin, and it has attained its full R conformation right over here in the lungs. Now when the red blood cells they travel towards the tissues, what happens is that the partial pressure of oxygen in the surrounding tissues, it decreases, and over here in the tissues, what is the partial pressure in tissues? It's pretty low. It's approximately uh, it's this indicated by this blue region over here, okay, in between 10 and 40. Okay, so this low partial pressure of oxygen, what it causes, the hemoglobin molecule, it causes the oxygen to be dissociated from the hemoglobin molecule. It removes an oxygen molecule due to the very low partial pressure, and also due to some other factors which we are going to discuss in the upcoming lecture. But over here what happens, that since the partial pressure, this is one factor that removes the oxygen from the hemoglobin. Since the partial pressure of oxygen in the tissues is pretty low, oxygen is removed from the hemoglobin, and once one oxygen atom is removed, then what happens is that the R conformation, it starts changing into the T conformation of hemoglobin. And because oxygen is now being removed, so the hemoglobin has begun attaining its orderly structure again. And in the last lecture we discussed this part as well, in which the ferrous ion, it moves into the plane of the protoporphyrin 9 when oxygen is bonded to it. So now when oxygen is being removed, this ferrous ion, it again moves out of the protoporphyrin ring, and it is then again not in the same plane as the protoporphyrin 9. And since if oxygen is not in the same plane as protoporphyrin 9, if the iron is not, the ferrous ion is not in the same plane as protoporphyrin 9, then the bonds start forming again, and then the hemoglobin start attaining a tense conformation. And once it attains a tense conformation, this tense conformation has a lower affinity for oxygen, and so it is unable to hold on to the oxygen molecules, and so the oxygen molecules are rapidly released from the hemoglobin molecule at the tissue. So this steep slope over here shown by this graph, it indicates that the hemoglobin has now begun changing into the T conformation. It has now started attaining the T conformation, and so it has lost its oxygen supply, and it has lost its oxygen to the tissues, and so the partial pressure of the hemoglobin, it decreases to almost zero. Why? Basically the saturation with oxygen decreases to zero. This is because now the hemoglobin has attained its T conformation, and T conformation has a very low affinity for oxygen, and it has unloaded all its oxygens. All the four molecules have been unloaded, and so they should have been unloaded because it needs to provide that oxygen to the surrounding tissue, which has a low or partial pressure of oxygens. Whereas if we look at the graph of myoglobin, the graph of myoglobin is not sigmoid, it is rather a hyperbolic graph in shape. Okay, it is hyperbolic. And even if in this blue region, if you look at the graph of myoglobin, myoglobin is still very highly saturated with oxygen. It has not lost its oxygen yet. So this means that even when the partial pressure has decreased over here, so this means that the myoglobin has a much higher affinity for the oxygen, even when the partial pressure has decreased to almost like 10 millimeters of Hg. Okay, so even at 10 millimeters of Hg, myoglobin still has a lot of oxygen with it. Okay, it still has its oxygen, and it has not lost all of its oxygens. And now when the partial pressure decreases even further, this even below 10 in the surrounding tissues, this happens when strenuous exercise is performed, or when the oxygen demand increases during exercise. So this is when the myoglobin, it supplies its oxygen, and so it is then removed from the myoglobin only in that condition, when the partial pressure of the surrounding tissues is very low. But if the partial pressure is low enough, even in this blue range, myoglobin will not supply its oxygen, and it will still hold on to its oxygen. So myoglobin has a higher affinity for oxygen than the hemoglobin, and this affinity is also important because now if we talk about the muscle cells, in the muscle cells we have myoglobin, which has to accept oxygen from the hemoglobin, so it has to have a higher affinity for oxygen than the hemoglobin, so that it is possible for the myoglobin to accept the oxygen molecules from the hemoglobin. All right, and then this is how why the hemoglobin attains this graph attains a sigmoid shape. It is due to this cooperative behavior of the different heme groups. Okay, the heme groups, they cooperate with one another. Okay, so when oxygen starts adding up, this heme group, it interacts with the other heme group, and so it makes the other heme group to accept the oxygen more easily. Okay, so that's why if we go in the forward direction, why is there a steep rise in the graph? There is a steep rise in the graph because now this happens in the lungs. Okay, when the deoxygenated blood has reached the lungs, what happens is that the hemoglobin, now the partial pressure of the surrounding tissue, it starts increasing, and so a very when the partial pressure of the surrounding tissue starts increasing in the alveolar airspace, since there is very high partial pressure, what happens is that the hemoglobin, it accepts the oxygen molecule, and once one of the oxygen molecules have been accepted, then once one oxygen molecule has been attached to one hemoglobin molecule, what happens is that it interacts with the other hemoglobin molecules, and it changes the conformation from T to R. Okay, T to R conformation channel change occurs, and R has a much higher affinity, so the subsequent hemoglobin molecules, they quickly and at a much faster rate accept the oxygen molecule from the surrounding tissues, and this is actually important so as to efficiently accept all the so as to efficiently get 100% saturated in the lungs. All right, and so now after accepting all the oxygen, then the percentage saturation reaches 100%, and that's due to the R conformation of the hemoglobin, and this is due to the T conformation. This decrease is due to the T conformation. Okay, so it's due to this cooperative binding of the hemoglobin that the sigmoid shape of the oxygen dissociation curve exists. Okay, whereas in myoglobin, the cooperative binding does not occur like this, like so like the hemoglobin, it does not have such a sigmoid shape because its cooperative binding is not like hemoglobin, and it has a much higher affinity, so it still has a higher oxygen saturation even in this blue region. And after the blue region have been passed, only then it supplies its oxygen to the muscles or to the cardiac or skeletal muscle, only when the demand for oxygen is very high. Now what is this P50? P means pressure and 50 means half. Okay, so when half the pressure, the partial pressure of oxygen which is required to saturate hemoglobin or myoglobin by 50% is known as P50. Okay, so P50 is a partial pressure of oxygen so as to saturate the hemoglobin or the myoglobin by 50%. Okay, when half of the hemoglobin gets saturated, that pressure is P50. And now if this P50 is lower, if this P50 is lower, then the affinity for oxygen will be high. Okay, why will it be higher? Because if it is lower, then this entire curve will be shifted towards the left hand side, towards the myoglobin graph. And as you know that myoglobin has a higher affinity, so this graph has shifted left to the left side. So the graph has the curve has left shifted, and this left shifting due to low P50 means that the affinity has increased. And if the and the vice versa is also true. If the partial pressure is high, then the affinity for oxygen is low, and in that case, if this P50 is low and if the P50 is high, then the affinity is low, and in that case we say that the graph, this curve, has shifted to the right, or right shifted curve will be obtained in that case. All right, so P50, this is important definition. You guys should know this term because it's we are going to use this term in order to describe the characteristics of hemoglobin in the upcoming lectures as well. Okay, let me read out this paragraph. Okay, by the way, this entire diagram is from your book Lippincott. Okay, so you can also refer to that. The oxygen dissociation curve for hemoglobin is the steepest at the oxygen concentrations that occur in the tissues. Okay, this blue part, they are talking about the blue part. It's steepest in this region, so that the hemoglobin can quickly release its oxygen to the tissues, and this permits the oxygen delivery to small changes of partial pressure of oxygen. Okay, a small decrease in partial pressure of oxygen will allow the hemoglobin to release its oxygen quickly, and small increase in partial pressure of oxygen will allow the hemoglobin to accept the oxygen quickly. This the reverse is true only in the lungs. Okay, and in the lungs it attains 100%. Then finally, okay, moving on, the partial pressure of oxygen needed to cause half saturation is known as P50. The higher the P50, the lower the affinity. This is an important relationship you guys should know. In other words, we can say that the more the graph is shifted to the right hand side, shifting to the right hand side would mean that this point has become greater. The partial pressure, the value of partial pressure has increased to cause half of the 50% to be have to cause 50% saturation in hemoglobin. So right shifting would actually increase the P50 value, and it will decrease the affinity for oxygen. Okay, hemoglobin has a lower affinity for oxygen. That's why hemoglobin is to the right of the myoglobin. It has a lower affinity, so hemoglobin also has a higher P50 than the myoglobin. Hemoglobin has a P50 of 26, whereas myoglobin has a P50 of just 1. Okay, so that's a big difference between the P50s of myoglobin and hemoglobin. So that's why the sigmoid curve of hemoglobin is to the right side of myoglobin. Hemoglobin has a lower affinity than for oxygen than hemoglobin, and then okay, actually wait, this isn't hemoglobin, it's myoglobin over here. Okay, this is myoglobin. Guys, please correct this part. This is myoglobin. Okay, myoglobin graph has a hyperbolic shape. Okay, this shape is hyperbolic, right? This is a characteristic hyperbolic curve. But the hemoglobin curve has a special sigmoid shape. This S-shaped curve of hemoglobin is the sigmoid curve or the sigmoid shape. Okay, and it's due to the cooperative binding, which we've discussed in detail in the previous lecture as well. The link to that has been given in the description. Do check that out. And for of the heme groups to the oxygen, cooperative binding of the heme groups to the oxygen. And if you still don't know what cooperative binding is, I would strongly suggest that please do check the previous lecture. Now A bit of the information about myoglobin. Myoglobin is a protein. Okay, it's also a heme protein, just like the hemoglobin. It's found in the muscle cells of skeletal muscle and cardiac muscles, and its role is to accept oxygen from the hemoglobin and store it for a certain time, and then gradually deliver within the muscle cells whenever it is required to deliver it. Okay, and this an example is when a person exercises. Okay, during exercise, this during exercise, this is required. The myoglobin, it provides its oxygen to the muscle cells. Myoglobin has a higher affinity for oxygen than hemoglobin in order to accept the oxygen from hemoglobin. Okay, if myoglobin will not have a higher affinity, if its affinity is going to be lesser than the affinity of hemoglobin, then it will not be able to accept the oxygen from hemoglobin. Okay, guys, so that's it for this lecture. From the next lecture, we are going to talk about the allosteric effectors and what these are in quite detail. Okay, these are basically those effectors which affect this oxygen dissociation curve. Okay, and we are going to talk about this in the next lecture, and I'll give the link to that in the description. Thank you so much.